Wait for it. Wait for it. Tick tock, tick tock, tick tock, tick tock. I'm watching my clock. The tension is rising. Wait for it. There we go. It's 2 hours UTC. And Astronomy Daily Live has begun for another day. So glad everybody could be here. Gonna wait a few minutes, see if anybody comes on in. Glad everybody can be here, either live or not live. Yeah, so this is just a daily gathering of friends, circle of friends. Gather around, pull up your chairs, grab your favorite consumable, and let's sit back and talk astronomy for an hour or so. So hope everybody's doing well. I'm gonna pull up the live stream on my smartphone. I've already got the the uh, uh, the chat there. Hey, Samantha, are you sure you're alive? How can you be so sure? How can you be so sure? I don't know. You know, Descartes said that he thinks, therefore he is. Maybe that's proof enough. Maybe that's proof enough. Hope you're doing well. So let's talk astronomy for a little while. We'll gather around a little bit. This is just a casual, fun get together where we talk astronomy for more or less about an hour or so every single day, same time, same place. Um, and we can talk about anything, whether you're new to astronomy or um, um, have done have done astronomy your entire life. This is the place. Uh, yeah, please state the nature of the existential emergency. Yeah, yeah. No, there's no emergency. In fact, Buckminster Fuller um, really, really liked the idea of the concept of emergence through um, emergency. So it's in those times of sort of strain and stress and peril that we really emerge. So yeah, I think that's a great concept. Check out Buckminster Fuller's book, Nine Chains to the Moon. Awesome, awesome, awesome book. It's actually very, very um, relevant to today. He wrote it. He published that in the 30s, in the 1930s, and it's still relevant today. Yeah, yeah, starter scope. So hope you're getting into it a little bit, Samantha. It's it's a tough choice. There's a lot of choices of telescopes out there, and I don't have any specific recommendations. I can just say start low and go slow. So and that'll help quite a bit. There's much to this science of astronomy, and you can sort of come at it from lots and lots of different angles, lots of different ways. Um, Whatever your budget is, whatever your style is, anything else. The probably, as I said, probably the most important thing you can do, um, maybe the two most important things you can do, um, um, since you're new, is to maintain your enthusiasm. Don't get too discouraged or let down or anything. That's really really hard, um, because getting into something new is always tough. But keep your enthusiasm high, um, and find a local club. Um, they usually have like monthly meetings where you can go. There's usually like a presentation of some sort, and if nothing else, you're surrounded by like-minded folks who love talking astronomy, thinking astronomy, doing astronomy, and get in with some of those, ask questions. Usually, members of like the local astronomy clubs are very enthusiastic about new people, bringing them into the fold and getting them engaged. And you'll find out about activities like star parties, which are really, really fun. You go out usually to a relatively dark site. It sort of depends, but get yourself out um, under the sky with a bunch of different telescopes. You can, try them all out, um, uh, all that. So, yeah, and if people aren't your thing, now is sort of the dawning of the age of what I'm calling uh, armchair or desk astronomy, because there's so much available right from here, right from these screens. Watch last night's live stream, Samantha. We looked at the sun for the entire hour, and all of these images, all this data, um, is just a click away. It's just, I mean, it's that easy. And if you're just there to look, that's great. If you're there, to actually do some science, you can do that too. There is data from all of the spacecraft, um, going back, to Pioneer, Voyager, Viking, um, up to the modern era, New Horizons, Juno, Cassini. All that data uh, is right there. So it's very very awesome. So yeah, and if people aren't your thing, get yourself, as I said, sort of a decent sized refractor. Spend $100 or so. It's not too much, I mean, even that, can be a chunk. You would spend $100, get yourself, you know, something relatively nice, and uh, on a clear night, look at the things that are obvious, the moon, planets, that kind of thing. What I did as a kid, uh, because I lived in the city, I I didn't have um, access to a dark sky. I mean, I was lucky to see third magnitude stars, right? With a telescope, you could see, you know, fifth or sixth magnitude or so. Well, there's lots of binary stars that are that bright. And I was just on Pamela Gay's CosmoQuest X Twitch stream, um, where somebody was talking about the star Zubinel. That's a star. It is the brightest star in the constellation of Libra, and that is a binary star that you can very easily see with a refractor. Um, and um, as a kid, you know, I was so enthusiastic that I observed this binary star, you know, every clear night for days and weeks, and I drew it, right, and I was absolutely certain, right, that I could see the secondary star going around the primary star just a little bit. I was really sure. I was really sure. But then, and this isn't the right uh, volume, but I had just acquired my my set of Burnham's celestial handbooks, and these are in 3 volumes, organized by constellation, um, alphabetically. Yeah, it's a mouthful, but it's great, and you will impress your friends. um, but I looked it up in here because Burnham's has just tons and tons and tons of information about um, stars, variable stars, galaxies, just, you know, lists, lists. I can hold, hold this up without destroying it too much. Lists of binary stars. Okay, just binary stars. And so I looked up Zubin Ganubi and realized that it takes about 1,000 years for the secondary to go once around the primary. And so I sort of decided at that point that probably I wasn't seeing it going around, you know, in a matter of days or weeks. So, but you know, the enthusiasm was there, and of course I was hooked. And so yeah, binary stars are a really great thing to look at, even from, you know, the middle of a large city. One of the stars in the handle of the Big Dipper is um, is a very complex binary star, in that the 2 stars that you can see, Mizar and Alcor, each of those stars is actually a binary star as as well, or I think multiple stars. I'm not exactly sure how many, um, but conceptual idea was to take my very cheap scope, point it east or west. Okay, yeah, your shot. Uh, yeah. You know, don't, as I said, you know, don't be discouraged much. Do what you can. As I said, you know, binary stars are a good start. Planets, of course, you're the moon. Um, yeah, start there, and you know, go from there. See if you can find, you know, some darker sites. You can make a little trip out to a darker site where, you know, you can look at um, some fainter sources. Yeah, it's sort of an adventure, right? And maybe you will catch the fever, and if you catch the fever, then you'll want to get a larger telescope, and then you'll use that for a while, and then you'll say, if if only I had something a little larger, and then you get something a little larger, and then you use that for a while, and then you go, now if I had something just a little bit larger, I'd be able to see these things too. And it just goes on and on and on. Now, I guess I was sort of lucky. I never got the fever because at a relatively early age, uh, by the time I was 19 or 20, I was working with professional size scopes. So yeah, I never actually got the fever. I'm actually much more interested in what one can do with sort of a modest size scope like this. This is a zero point 0.2 meter telescope. It's an 8-inch telescope, Celestron Nexstar 8SE. And I'm actually doing a project now um, trying to figure out how well this system works for doing astrometry, which is the measuring of the positions of targets of the sky, and also photometry, which is the measurement of the brightnesses of targets in the sky. And I'm happy to report that um, uh, things are looking pretty good on both of those fronts. I was having a little bit of difficulty understanding my photometric results, but now I think I have a pretty good grasp of what I'm seeing and why I'm seeing it, and so I'm pretty happy. I'm pretty happy. Um, I need to look at more data. See, astronomers and scientists in general always want more data. Well, I've actually got it. I did an observing run with this a few days ago, maybe almost a week ago or so now, and collected a bunch of data under different conditions. Um, I had a session a couple of weeks ago, my evening of March 15th, and seeing conditions were pretty poor, um, and I'm seeing that in the data. That's what I think was sort of confusing me a little bit. I'm going to get rid of that. That wants to slow me down. Apple software wants to update, and I just gonna ain't ain't gonna do it. So actually, if you can just start taking holidays, yeah, and make sure that as the size of the telescope grows, um, make sure that you can still haul it around. I'm lucky enough to live in a place that it's all I have to do is carry this thing outside. I don't have to pack it. I don't have to move it. I just have to lift it outside, and I'm under some of the darkest skies on the planet. So luckily enough, but yeah, make sure that um, whatever you have is portable, right? You got to be able to lug it around, or at least be willing to um, lug it around. But yeah, you know, be patient, keep your enthusiasm, and you'll do great. You'll do absolutely great. Um, yeah. I remember, the first time that I ever saw a dark sky, a really dark sky, and I can tell you that for a while, for quite a while, that evening, I was lost. I was really lost because there were so many more stars, you know, sort of confusing things that I was just, I was completely lost. Didn't have a clue where things were. Took me a while, to get my bearings. But now, as I said, lucky enough, to live. I'm in a place where I've got extremely dark skies, and that was done on purpose for sure. Um, yeah, cool. Yeah, the load weight. Yeah. Well, start with a refractor. As I said, spend $100. See if you even like it. You sort of have to get over that hump. See if you like it first. If so, then you can sort of decide on a path, whether you want um, to go on a path of just sort of looking, or um, or if you want to get into like photography. Those are sort of two different paths, and you'll choose telescopes depending on those paths. Um, or you can do both, right? You don't have to choose one or the other, but yeah, your choice of telescopes, at least at the beginning, you're going to have to sort of choose, which way you're going to go there first. But yeah, yeah, very cool. So what I wanted to do tonight, one of the things that Space TV last night, I think it was last night, was asking me about my favorite space movies. And my wife reminded me this afternoon that it is the 50th anniversary of Kubrick's 2001: A Space Odyssey. And I guess they're going to be re-releasing that in the theaters. And I've been told that we are going to go and see it um, in the theater. Now, that's probably that is definitely one of my favorite space, um, you know, space related movies of all time. And I'm a big fan of Kubrick um, um, generally. His movies I find to be extremely well done for the most part. Um, Pretty good stories. The cinematography is is the thing that really blows my mind when it comes to Kubrick, and also, you know, sort of the situations. Um, I'm thinking of certain scenes in like Eyes Wide Shut that um, are just done so incredibly well. Um, the the scene where um, he meets up with the piano player at the bar, and the piano player gets this phone call, right? And he's like, "Yes, sir. Yes, sir. Yes, I know where that is. Okay, thank you." And that's it, right? And it's like, everybody watching this is thinking the same thing. It's like, what are you what is this all about? And so you find out, right? And it's just, you know, great. Actually, my favorite Kubrick movie um, is one that very few people have actually heard of. Um, it's called oh, it's not coming to my head. Oh yeah, Barry Lyndon. Barry Lyndon. Probably my favorite, except for 2001. Um, Probably my favorite Kubrick movie. The acting is exquisite. The cinematography is just, I mean, gives me goosebumps. It's just, it's done so well, and the the scenes and the situations um, are just uh, um, uh, they're just absolutely fabulous. The whole thing is really really great. It's a very um, it's a pretty long movie, and it's pretty depressing, I guess. But if you overlook that, you know, overlook the fact that it's a little bit long, which I don't mind because it's so well done. It's so well acted. The story is so great. And as I said, you know, the cinematography is just it's like it's awesome. It's absolutely awesome. So anyway, check that out. Barry Lyndon. Um, um, Full Metal Jacket is intense. It's just awesomely uh, intense. And again, you know, the cinematography is fabulous. Is absolutely fabulous. And of course, 2001 is is you know equal to that in terms of you know the scenes, how it's filmed, the angles, the acting, the dialogue, um, just the whole thing, and the um, and the music. You know, the music in 2001 is absolutely stupendous. I guess as as the story goes, um, uh, the there was an original musical score that I think was all classical music. I think, and Kubrick heard it and is like, no, 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 no. We need something else. We need something else. So he hired I forget his name. You know, the scene where they're going down into the crater on the moon and they found, you know, the monolith. You know, they have it all dug up, and it's just the music with the voices singing. That's just awesome. That's just intensely awesome, and it fits so well. The other scene that I really like there is the music when Discovery uh, is going out to Jupiter. It's the saddest, loneliest music in the universe. It's just, you know, empty space and just alone, just so absolutely alone. And yeah, it's just great and sad, just sad, but just intense, just really intense. So yeah, 2001: A Space Odyssey for sure. Now I've neglected to mention that tonight's drink of choice is hydrogen hydroxide, HOH. So cheers. Hey, Samantha, check out slooh.com, slooh.com. For a monthly subscription, you can uh, take images with moderately large telescopes, 14-inch, 17-inch. I think the largest is like a 20-inch. They have 5 telescopes at the Canary Islands and 1 in Chile. And I think they have a solar telescope too. Um, you can subscribe to this service and you can create a what they call a mission, where you basically say, um, okay, telescope, and these are robotic telescopes. You can tell a telescope where to point and when, and exposure times and all that. Um, and you can do photography uh, from your home um, using a telescope at a very, very, very dark site. And it's very, very awesome. It's a great business model. Seems to be extremely popular. And for like $5 a month, I think you can take 1 or 2 pictures, and then for $25 a month, I think it's unlimited. So yeah, as I said, it's a great business model. Check them out. I think it's slooh.com, slooh.net. Let's share my screen, and we'll go over to their site. I don't remember if it's slooh.com or slooh.net, so we'll find out. We'll find out. Let's see. slooh.com, slooh.com. Now, you can join for free. So you just have to sign up, right? You just have to sign up. And I've done that. If you don't actually sign up, you don't really have access to a lot of things on the site. But I think I think I signed in as Cosmic Lettuce, if I remember right. CE, and I think I used that password. See if I can get in here. Oh, sign in error. Cosmic Lettuce. Oh, email. Okay, Cosmic Lettuce. Probably I used my email. Cosmic Lettuce at gmail.com. They have all sky cameras. You can check the status of the telescopes, whether they're open or closed. Yeah, it looks like I'm in. It's very awesome. It's very, very awesome. Of course, I don't have any observing log yet, but here are some images that looks like were just taken a while ago. This is of a pair of galaxies, interacting galaxies, just taken, right? April 3rd at 21:53 UTC. So that was like what, 5 hours ago, something like that. Let's see, how can we let's see if there's a anyway, so definitely check this site out, Samantha. You may want to get involved with this, because you know you can take, I mean, if you're into, you know basically just taking pictures, um, which is extremely awesome. There's a picture of the sun. There's a picture of Pluto, apparently. Huh. Don't know which one is Pluto. Saturn. Pretty good shot of Saturn, I suppose. There's the Trifid Nebula. You can take images using different filters, and then I think they have software online, or you can use Photoshop to combine them and make color pictures as well. So very, very awesome. Let's see, there's another wider field view of the Trifid. And then these guys also do live streams at least a couple each week. So check them out on YouTube as well. It's, yeah, just look for SLU. NGC 2451 open cluster. I'm not seeing an, yeah. Well, maybe it's a very, very open cluster. Very open cluster. Yeah, it must be. Wow, there's a bright something in there. It's a galaxy, NGC 3621. Anyway, yeah, so, check these guys out. They, pretty nice. And let's see, you can look at the telescopes here. See, there's one in Chile. It says it's green, which probably means it's open. And then there are 5 scopes on the Canary Islands. It looks like 3 of them are open and 2 of them are closed. Let's look at Canary 3 just for fun. Okay, so somebody's doing a deep sky observation right now of M91. Very cool. Let's see. So here's an all sky view from Canary 1, 2:31 UTC. So this was just 6 minutes ago. See a nice bright moon. Oh, but you can see the Big Dipper here, right? You can see Arcturus, Spica down here. Here's Leo over here. Here's Regulus. So yeah, that's the real sky. Oh yeah, they even have a time lapse movie. Check that out. There's the sun, it looks like. So it probably shows, the past 24 hours or so, something like that. So it's been nice and clear over on the Canary Islands. There's a few clouds going by there. Okay, here we come at sunset. And here comes the stars. Ooh, wow. Orion and Sirius and Leo right on the meridian. So yeah, these guys are doing it right, and I'm serious. These guys are doing it right. I'm extremely impressed, and I think it's a neat model. I'm kind of interested in knowing, how scientifically valid this um, um, uh, um, data is, because that's sort of where I'm coming from, is more from the science. Um, but I'm sort of keen on maybe doing a month-long subscription, grabbing a few images, seeing if I can do some photometry, and just see sort of how good they are. Compare it um, to my um, system. Yeah, there are a few of these um, automated telescopes. There's SLU, there's iTelescope. Um, there's a couple others you might want to do a search around, but SLU I found to these guys really seem to be on top of things. And $5 a month, that's not bad. It's not bad, if you just want to take a couple of pictures from a dark site. I think it's awesome. I don't know where this is going. Okay, let's look at Canary 2. Let's see what Canary 2 is looking at. So it's just looking at some portion of the sky. You can see that there's some flat fielding problems here, some bad columns, blah, 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 blah. You can take all that stuff out if you plan things right. So it looks like, yeah, this is just sort of someone has instructed the telescope, to look at a particular place in the sky. And yeah, looks like next at 250 UTC, they're going to be moving to M14. That's kind of cool. But you can see that this thing is going like every 5 minutes, it's going somewhere else. So yeah, it looks like a busy place. So yeah, not quite sure what Kevin F is observing here, but those look like pretty good images. Not too bad. Not too bad. Have to deal, with calibrations and all that, but not too bad. Let's see what else we got here. So this is the 2001 Space Odyssey. So yeah, just a reminder about that. Let's see what else did I what else did I do here? I was thinking about supernovas today a little bit. We can get into those if you want. I'm trying to remember what else. I think I had a link to that. Yeah, I was looking at supernova remnants. So supernovas are these exploded stars, and they sort of come in two different flavors. Let's just go to the Wikipedia page here. That's usually the easiest route to go. So basically, two kinds of things will cause a supernova. Um, both are sort of based on the same thing happening, but sort of two different ways. So a type 1 supernova is starts out as a white dwarf star that um, is orbiting a larger primary star. So the white dwarf is this small Earth-sized but very, very dense object that is orbiting a larger star, maybe a star like our sun or larger. Doesn't really matter all that much, but because of the proximity of the white dwarf to this other star, actual material is being transferred from the primary star onto the white dwarf star. Um, and if enough material falls onto the white dwarf star, it can actually get enough mass to allow its core to collapse. And when that happens, um, there's sort of a bounce back and an explosion. And that is a type 1 supernova. Now, there are details about that as well, but what I'm going to do is I'm going to actually go to the paper that I was looking at here over on archive.org, which of course is the latest and greatest uh, um, bleeding edge astronomical research. Because what these guys have done in this very long paper, this is like a 29-page paper. They've um, they're interested in looking at the remnants of these supernova explosions to sort of see if they can figure out from, you know, what they're seeing in the debris to figure out what kind of supernova it was. Now, the second kind of supernova that can happen is what's called the type 2 supernova. And that's when a single massive star, usually, you know, five, 6 times the mass of our sun, you know, maybe 10 times the mass of our sun, just a single star, it has so much mass that uh, uh, when when the nuclear fuel supposedly inside of the star runs out, then of course, you know, that pressure keeping the star uh, big and expanded diminishes, then all that matter starts to fall in, and you have a collapse of the core as well, and a bounce back and an explosion. So that is basically um, a type 2 supernova. Um, so type 1 is usually in some kind of a binary system where you have a white dwarf that explodes. Type 2 is a single star, massive, that explodes. And so what these folks were interested in is they were looking at, you the remnants of supernova explosions that, you know, happened hundreds or thousands or tens of thousands of years ago, um, trying to understand. It's like, okay, you know, this is what we're seeing now. Can we sort of run the clock back and um, try to understand, you know, what what kind of supernova it was, what were the circumstances, um, et cetera, et cetera. And you know what they want to do is they want to feed this observational data into their models, because it's the models that allow you to run time backwards and see, you know, what happened earlier. Um, so, so I'm just going to go. I looked at this a little bit earlier. Um, uh, So yeah, they do have a focus on a supernova remnant called Cassiopeia A, which is relatively close. It's only 3.4 thousand parsecs away, which is let's see, let's put that into light years. So a parsec is 3.26 light years times 1,000, which is a kiloparsec, and then multiplied by 3.4. So that's about 11,000 light years away. So very, very, very close, very, very nearby, and relatively young as well. They think it exploded about 350 years ago or so. Um, so let's see. Yeah. So the morphologies of supernova remnants are complex and varied. Um, and what they've been doing is they've been looking at these supernova remnants um, at different wavelengths of light, from X-ray to radio to optical, um, infrared, ultraviolet, all of it, all of it. Um, and I guess what they're talking about here is that they've observed, sort of two main categories. That there are these shell these shell type center field, and then a composite of the both. So shell type, you can sort of imagine, when the star explodes, it just sort of blows out all of its stuff. And so over time, you just have this expanding shell of material. But you can also have this other kind where there's not so much of a shell, but just like this stream of material. Or you can have a combination of both. And so here they show some examples of some supernova remnants, all different kinds. Um, See, this would be more of like a shell type, and this would be more, what do they call those? The center field. So here, well, this is like a composite, right? Because it has a shell on the outside, and then there's also, the stuff on the inside as well. And then you have these kinds of things where it's just complicated, complicated things. Here's the Crab Nebula supernova remnant in X-ray. Here, I recognize that. But yeah, what they're trying to do is they're trying to look at look at the characteristics of these shells and of these center field things, and try and get a grasp on, okay, did this originate as a type 1, or as they're calling a core collapse, or a type 2. Um, so the most reliable ways to classify explosion types are a detection of a neutron star. That's not always possible because apparently the neutron stars um, get kicked out because the explosions aren't symmetric. So you sort of have the explosion is maybe on one side. So the neutron star that's actually produced as a result of that collapse can actually get propelled out. Let's see. I'm zoomed in a little bit too much here. Detection of a neutron star or a spectrum from surrounding light echoes. Another means to constrain the progenitor star is to measure the number of OB stars, which are young hot stars. Um, uh, so yeah, this is when it gets into looking at the chemical constituents of these remnants, and you know uh, the chemicals will glow at different wavelengths of light. Some of them in the X-ray, some of them in the optical, some of them radio, all over the place. So it's useful, to look at these in as many different wavelength realms as you possibly can. Um, Literature measured and compared the morphological asymmetries of the silicon 13 images. So 13 times ionized silicon glows in the X-ray. Um, these authors found that type 1a supernova remnants are more circular and symmetric. So if you look at these supernova remnants and find, you know, nice round um, structures, what they're saying is that it sort of looks like maybe it's a type 1 as opposed to a type 2. Type 1a. Yeah, very cool. So yeah, it looks like they've sort of concluded here already that the type of explosion, whether it's a type 1 or a core collapse, as they call it, um, have different shapes. Let's see. It's worth noting that systematic analysis of iron K shell emission in type 1A and core collapse supernova remnants recently showed that the iron potassium alpha centroid can also be used to type supernova remnants. Huh. Okay. Neutron stars are thought to possess a substantial kick velocity, as I was saying, due to the fact that these um, core collapses aren't really symmetric, right? The explosion will happen sort of on one side, and so that'll just um, um, propel them uh, with high velocity, 1,000 kilometers a second. That's pretty serious. Um, Abilities lead to asymmetric mass ejection, right? Uh, Another set of models, the kick arises from neutrino emission. In this case, okay, yeah. Regardless, these things are being propelled violently when they explode. And, but that makes sense. You can't imagine that these explosions, would be completely symmetric, right? Uh, Nothing ever is. So here's just sort of a chart of 6 supernova remnants showing that uh, these green arrows are showing where sort of the bulk of the material is moving, and the white arrows are showing which way the neutron stars are moving. So makes sense, right? Most of the propellant is going that way. It's just like a rocket, right? Most of the propellant is going that way, and so the object goes that way. But look at this one. there's always there's always the white crow, There's always a white crow. It's bound to be some kind of contrarian in there to mess up all of our theories. So these are just multi-wavelength um, images that have been colorized, to bring out features. That's always nice to see. The persistent elongated morphologies of jet-driven supernova remnants. So here's just some models that they ran, simulations. I'm getting to a couple of plots that I found pretty interesting. I'm just going to go down here. Instabilities and mixing, Collateral supernova remnants, and the galactic magnetic fields. So they actually found that the that that, that the structures of these supernova remnants sort of lined up with the galactic magnetic field. So, not only do you have local interaction, you know, um, a lot of these stars, they explode in places where there are many other stars, lots of gas and dust. So you have that kind of interaction, but you also have the galactic magnetic field that is interacting with these things as well. So just absolutely amazing stuff. All of all of well, most of this information that um, is in this paper is extracted from spectra. Um, Spectra have just tons and tons and tons of information in them. Um, just a huge amount of information about how this gas and dust moves, what it's made of, how fast it's moving, how how much stuff, what stuff it is. It goes on and on and on. These I thought were some pretty interesting plots. So they've actually measured the velocities of this gas and dust in different places and at different wavelengths, and they can actually measure the velocities of these things, sort of line of sight. So at least how I read this is that it's as if we were looking at this supernova remnant from this direction. So looking at it that way. And what we see is that the material is expanding out that way. not expanding that much out this way, at least relative to us, and of course expanding out that way relative to us. So this stuff is sort of coming towards us. This stuff is going away from us, and this stuff seems to be moving outward, tangentially to us. And it sort of depends on what stuff you're looking at. The red dots here are argon 2, and the black dots here are silicon 2. And over here, we're looking at, let's see, the green is iron, potassium, and the black dots here are uh, silicon ionized 13 times. So, lots of energy there, lots of energy. But so yeah, so we're starting to get an idea of the 3D structures of these things. So that's very, very cool. And they even have some pictures of those as well. So this is Cassiopeia A, and this is normally what you see, just this stuff. But what they found is nitrogen and oxygen, and S is sulfur. Isn't that sulfur? Isn't that S? So they're finding all kinds of chemicals out here that are apparently emanating from this supernova remnant. And of course, the theory here is that it's primarily supernovas that do generate the heavier elements that make us and make a lot of the things on Earth. In fact, all the things on Earth. Carl Sagan said that we are star stuff, and this is sort of where it seems to start, is when these stars explode and blow out all this stuff, right? Nitrogen, oxygen, sulfur, it's all there. It's all there. Here's some 3D models. I think the red and the blue are showing velocities. So that's like a red shift and a blue shift. So the red stuff would be moving away from us, and the blue stuff would be moving towards us. And so they can rotate this around to sort of get an idea of the 3D structure of, I think in this case it's Cassiopeia A. Yeah. A little bit more of those. So iron, they're looking at the iron, which emits in the X-rays in this case. So as I said, this is a long paper. I don't think I'm going to dive into it much more. One thing I wasn't aware of was this jet coming out of the Crab Nebula. I have to look into that a little bit more. I didn't know that there was a jet coming out of that. All right. Well, I think we are definitely past our hour. So I think that I'm going to call it for the evening. Glad everybody could come by. Make sure to subscribe, hit the thumbs up or the thumbs down. I just like a reaction. Make some comments if you have any kinds of questions or topics. Let me know. You can definitely send me an email, cosmiclattice@gmail.com. And yeah, I think I'm going to get out of here for this evening. But we're going to do it again tomorrow. same time, same place, 2 hours UTC, talk more astronomy. You know, there are so many things to talk about and think about that this is easy. It's easy, you know, to do a daily thing because there's always, you know, science of astronomy is sort of the science of everything. So we can talk about everything. All right, I'm going to get out of here for now. Have a great evening. Great day tomorrow. I will see you on the spin, 20 million kilometers somewhere out there, and 23 hours, a little less than 23 hours to go. All right, take care, everybody. See you tomorrow. Bye.